Alright, so here's hopefully the shortest video. For problem 1 in my worksheet on simulation, I asked you to generate a list of 10 random numbers. I'd like you to use the Linear Congruential Model. Now, this model basically requires that you have a starting number and you have different variables. So there's x sub I plus 1 equals a, x sub I plus c, modular m. In the problem I've given you, I gave you a, c, m, and x sub 0. So pretty much you have everything you need to start. If you're not sure how to do modular arithmetic, you can always plug that into Google and say mod 100 in front of whatever number you have, and it'll give it to you. Or, since this is modular arithmetic, essentially whenever you get an answer, ignore anything beyond the hundreds place or including the hundreds place, and really only look at the first two numbers in a number. But if you're to this level, I assume you probably know about modular arithmetic already, quite a lot. And modular 100 is really easy. So, for this first one, it's 17 times 31 plus 43 modular 100. So, you take out your calculator, and this is based off of what I plugged into my formula. 17 times 31 plus 43, that gives me 570. As this is mod 100, that means my result is actually 70. I can ignore the 500. So, now moving forward, I plug that 70 into this space. But see, the a and the c and the m still remain the same. A is still 17, c is still 43, and m is still 100. But it relies on the last random number generated. So here, I'm going to plug in the number 70, and then I'm going to say 17 times 70 plus 43, well that's 1233, or 1233. I can ignore the 1200, and I can just make this equal to 33. Continuing forward, I'm going to say 17 times 33 plus 43. Now that's going to be mod 100 as usual. So what's that going to be? Well, that's going to be 17 times 33 plus 43. It's going to be 604. Let me go ahead and write it out this time. 604 mod 100. So in this case, you just drop the 600 and you ignore that 0. If you want, you can also think of it as subtracting by 100 enough times until you get to a number that you can't subtract to anymore, until you get like negatives. So this would just be 4. So it's you see how it's the idea of randomness. Like the first number, 31, is sort of similar to the third number in this case, x sub 2, 33. It's very similar, but it's still randomly generated, and now it's led to 4. We'll do one more. So x sub 4. Once again, it's going to be 17 times now 4 plus 43 and mod 100. So what's that going to be? Well, let's check it out. 17 times 4 plus 43. That's going to be 111 mod 100, which is the same thing as 11. So, basically all this is asking you to do is continue doing this until you've gotten 10 of these numbers. It's up to you if you want to include x sub 0 as one of your numbers. It's a really simple exercise. It's really just plugging it in. It reminds me of like a Fibonacci sequence where it relies on past numbers in order to continue on, except it's a little bit easier. Fibonacci sequence requires you to know 2 of the past numbers. This only requires you to know 1 of the past numbers. When it comes to generating random values, this is really important in simulation theory. Simulation really requires the idea of true randomness, but we can't really get true randomness with a computer, so, and even in real life in ways. So we can only do our best attempt at getting a random number. And this is a Monte Carlo sampling method, and the linear congruential model is just a part of that. And that's just one way we might decide to generate random numbers. In problem 2, you'll be using this similar method, and then you'll be taking averages to decide different values. And in problem 2, you're going to actually see, if you would like, I'll explain it in the video, basically you can continue doing it more and more and more to get more accurate results. But keep in mind that throughout simulation, it's very different from just optimization. Optimization is saying this is the best amount of money we can gain, or whatever your situation is. Simulation is kind of like running a risk and trying to minimize all that risk. It's similar to the idea of optimization, and it can be used to test an optimization model, but it's definitely got its hands tied in the way of optimization. It's not considered an optimization technique because you're really just going to be finding like average values. But that's still very useful, especially if you're in a stock market, for example, and you need to simulate a stock market so that you can know what the best choice is for investment. And it may not be the best choice, but you know it'll be a safe choice. This is kind of what simulation can lead to. Luckily, we don't have to worry about the computer side of things. We're just dealing with the math behind a lot of it, and that's going to lead to a lot of random number generation. And we'll start getting into inverse transform method and acceptance rejection method, which are just fancy ways of kind of converting between CDFs and PDFs in statistics. And that's going to be similar to like integrating piecewise functions in calculus. So, hope you enjoy this series. See you later.